Okay. Yeah, good morning, friends. I welcome to the GATE classes on mathematics. I am Dr. Deekshitulu, Professor and Head, Department of Mathematics, University College of Engineering, Kakinada, JNTU. So, I welcome you all to these classes on mathematics for GATE. So, first of all, let me humbly explain you. We have 3 or 4 different courses of mathematics in the BTech, and here we have a stipulated time stipulation there, around 12 to 14 classes. So the basic concepts we go a bit briskly, and then we'll go to a better depth of the content in a leisure way. So the syllabus for all branches is almost all 80 to 90% is the same, but for branches like CSE and IT it is completely different. But for all other branches it almost all goes in the same lines. So I have prepared my presentations with respect to the common topics for all the branches. Say for example calculus and numerical methods and all these concepts are common for all the branches. So first we will go through the common topics, and then we will go to specific topics like discrete structures or something like that. So first I start my talk with calculus. I tell you once again, this calculus is common for all branches. So in calculus we have different topics like limits, functions, limits, continuity, differentiability, integration, and then improper integrals, then partial differentiation, then multiple integrals, vector calculus, and then Fourier series for some branches. So it's a huge stuff here in calculus for us. So I just go through the basic concepts. I brush up these things once, basic calculus like limits, continuity briskly, and then we'll go to the topics like multiple integrals in a leisure way. First, so calculus. So what is a function? First thing. A function f from a set D to a set Y is a rule that assigns a unique value to f of x in Y to each x in D. So D is called, we know that, a domain, and Y is called codomain. So for each element of the domain there must be an image in the codomain. That's what we say, assigns a unique value f of x. It must be unique. You cannot have 2 images in Y. In Y, then D is called, then f is called a function, and the set of all values of f of x in Y is called range of f of x, and then clearly range of f of x is a subset of Y. In certain cases the range of fx may be equal to codomain also. So this is the basic principle in the simplest possible terms. So if y belongs to y and y is equal to f of x is a function of d to y, then x is called an independent variable, because the calculus always deals with, the main purpose of learning calculus is how a dependent variable behaves with respect to a change in independent variable. If anybody asks you what is calculus, straight away I can answer. It discusses the behavior of the dependent variable with respect to the independent variable, and that is calculus. So x is called the independent variable and y is called dependent variable. If both x and y are real numbers, then f of x is called a real valued function of real variable. So then coming to a specific issue is a natural domain. Sometimes the functions may not be given a domain or this thing. Then in such case, if no domain is given explicitly for a given real valued function, then the domain consists of all real numbers for which f of x yields a real value. So f of x, if it gets a real value for any x, then you can consider all real numbers, then it's called a natural domain. Say for example, if you consider the example of the domain and range of f of x is equal to 2 plus square root of x minus 1. So here for x less than 1, what happens? Can we have a natural domain here? No. Why? for x less than 1, square root of x minus 1 becomes imaginary part. It is the function f of x does not yield a real value. So in such case, that means for x less than 1, f of x is not real valued function. So that part of this real number system is eliminated. So since no domain is stated explicitly, domain of f is a natural domain, that is 1 to infinity here. The natural domain is 1 to infinity. For x less than 1, square root of x minus 1 is not real. So the range of f of x is 2 plus square root of x minus 1. When x is equal to 1, f of x becomes 2. And then when x is infinity, it becomes infinity. So the range becomes 2 to infinity, closer to infinity. Similarly, if you take the other example, x plus 1 by x minus 1. So natural domain here is when x is equal to 1, what happens? F of x goes to infinity. So function is not defined. So delete it. We delete this x is equal to 1 from the natural domain, and the domain becomes minus infinity to 1, open 1, union, open 1 to infinity. That means for all x other than x is equal to 1, f of x is very well defined, and then the range is again minus infinity, open 1, union, open 1, infinity. So this is a simple example for this thing. So one more thing that most of the students, they don't understand the difference between family of curves and equation. So you have a lot of difference between these two. This family of curves is a very, very important concept in almost all mathematical ideas and engineering concepts also, wherein the surfaces, integral surfaces are in fact defined by, generated by the parameters or arbitrary constants. Let us see how this family of curves, what we mean by this family of curves. Constants that are allowed to vary are called parameters, and they make things more general in the geometrical sense. For example, if y is equal to m of mx, we know that y is equal to mx represents a straight line passing through origin, and if m is a constant, given, let us say if we take m is equal to 1, then y is equal to x, we know that it's a straight line passing through origin with slope 1. But if in place of m, if I go on changing the value of m, m is 0, 0.1, 0.2, 1, 10, 15, 20, 100, then what happens? All these things, they generate different straight lines. Together, this y is equal to mx represents an infinite number of straight lines corresponding to different values of m. But all of the straight lines have the same common property. What is that? They pass through the origin. So all the straight lines passing through origin are called a family of straight lines with common property passing through origin. So what is the difference between y is equal to x and y is equal to mx? Y is equal to x, the coefficient of x is fixed as 1. But if m is a variable or it is allowed to vary, just like it's a parameter or arbitrary constant, sometimes refer to it as a arbitrary constant, then y is equal to mx represents family of straight lines. All these lines produced are called family of straight lines with a common property, that is passing through origin. These parameters are also referred to as arbitrary constants. Another example, if you see, x square plus y square is equal to 4 is equation of a circle centered at 0, 0 with radius 2 units. All of us know that. In place of 4, if I put some a square and I call a is a parameter, then what happens? If you take a is equal to 1, you get one circle. A is equal to 2, another circle. A is equal to 4, 9, 16, 20, 30, 30, 40, 100, 100. So many circles you get. All are centered at 0, 0. So x square plus y square is equal to a square, and if a is a parameter, now it represents all the circles centered at 0, 0 with different radii. So that represents a family of circles centered at 0, 0 and having different radii. That's what we mean by a family of curves, and the main difference between a single curve and a curve involving parameters. Next, Then I'm just going quickly through the functions because all of you are well aware of these ideas because one functions, onto functions, by exponential functions, logarithmic functions. You have done enough of that. So just I'm going briskly to these concepts. The functions f and g satisfy the two conditions. G of fx is equal to x for every x in domain of f, and f of gy is equal to y for every y in domain of z. Then we say that f is an inverse of z and g is an inverse of f. So I repeat, if g of f of x is equal to x for every x in domain of f, and f of g of y is equal to y for every y in domain of z, then we say that f is inverse of z and g is an inverse of f. Let us see an example in a better way. So if I define a function y is equal to x cube plus 1 and x is equal to cube root of y minus 1. So if you call this x cube plus 1 as f of x and cube root of y minus 1 as g of y. Now let us see, verify the conditions, above conditions that we have mentioned, the definition. So what is g of x? F of x is equal to x cube plus 1, put it in g of y. So that becomes cube root of f of x minus 1 or cube root of x cube plus 1 minus 1. If you cancel 1, that is cube root of x cube, same as x. Now see the definition once, before the definition of inverse functions. G of f of x is equal to x. So this condition is satisfied. You see the second one. F of g of y. That means f of x is x cube plus 1. Substitute g of y in that. That is cube root of y minus 1 whole cube plus 1. That is y minus 1 plus 1. If you cancel 1, again you get y. So f of g of y is equal to y. So that means both the conditions are satisfied. G of f of x is equal to x and f of g of y is equal to y. So that means f inverse of fx is equal to x and g inverse of gy is equal to y. Clearly a domain of f inverse is range of f and range of f inverse is domain of f. This is how we can verify this invertibility of functions. So method to find the inverse of a function. The function y is equal to f of x, then solve for x as a function of y. That means let us say x is equal to g of y, then g of y inverse of a. So for example, f of x is equal to square root of 3x minus 2 or y is equal to square root of 3x minus 2 implies x is equal to 1 by 3 into y square plus 2, or f inverse of x is equal to 1 by 3 x square plus 2. Question now, is it true always? Can we find the inverse of a function like this always? Are there any failures? Yes, we do have some cases like this. The above method of finding inverse fails in two reasons. First thing, f may not have inverse, then we cannot do anything. Then f may have inverse, but x cannot be expressed explicitly as a function of y. Such functions we call them as implicit functions. Then x cannot be expressed in terms of y, neither y in terms of x. Then finding conditions for existence. So is it to tantamount saying that if f is not an implicit function, is not an explicit function, then can it not have a inverse? Then that's an issue. So we have to answer the question now. Thus, finding conditions for existence of inverse or function is important, even if it cannot be found explicitly. So even if the function cannot be expressed explicitly, even then we can find inverse of a function. So then we have to find the conditions for the existence of inverse, even if the function is not explicit. Let us see. A function has an inverse. It's a theorem, important theorem in analysis. A function has an inverse if and only if it is one-to-one. That is, the function assigns distinct outputs to distinct input. What do you mean by a one-to-one function? A function is one-to-one if and only if for different points in the domain you have different images. Saying that f of x1 is not equal to f of x2 whenever x1 is not equal to x2. Whenever x1 is not equal to x2, that means two different points in the domain x1, x2 which are not equal. Then if you consider their images, they are also not equal. Such functions are called one-to-one functions. So coming back to the definition once again, theorem once again, a function has an inverse if and only if it is one-to-one. If it is a one-to-one function, then it has inverse. Let us see the geometrical sense. You understand, if you want to understand this theorem clearly, let us see the geometric meaning of this. If they this is called horizontal line test. F is one-to-one if and only if the graph of y is equal to fx is cut at most once by any horizontal line. If you take y is equal to f of x function like this and then draw any line parallel to x-axis, if you consider, if that line cuts the curve at most once, that means maximum one time, then it is called one-to-one. So in this particular diagram, if you see, so x1 0 and x2 0, if you consider these 2 points and if you draw the line parallel to x-axis, clearly this line cuts this curve at 2 different points, at x is equal to x1 and x is equal to x2. That means at 2 different values of x, that is x1 and x2, this f of x is having the same value. So f cannot be called as a one-to-one. So now we can understand the meaning in a better way. F is one-to-one if and only if the graph of y is equal to f of x is cut at most once by any horizontal line. Another example, if you see here, fx is equal to x square. The graph is like this for x1 minus x1 and x1. And if you consider any straight line parallel to x-axis, it clearly cuts the parabola at 2 different points. Let us say minus x1, x is equal to minus x1 and x is equal to x1. So we have the same image, the value of f of x at 2 different values of x is equal to minus 1 and x1. So this cannot be called as a one-to-one function. Another theorem now, if f has inverse, then the graphs y is equal to fx and y is equal to f inverse x are reflections of one another about y is equal to x. That is, one is the mirror image of another with respect to y is equal to x. Y is equal to x is a straight line passing through origin. So for example, if you take y is equal to x cube and if you solve for x, as I said earlier, then x becomes y power 1 by 3. So that is your image of inverse of y is equal to x cube. So f inverse of x is equal to g of x. If you call that as g of x, that is x power 1 by 3. And if you look at the diagram now, y is equal to x cube and g of x is equal to x power 1 by 3. They mirror images of one another with respect to the straight line y is equal to x. That is another geometric meaning of the inverse of a function. Let us see if you take y is equal to 2x again, if you have that simple straight line y is equal to 2x, or x is equal to y by 2, or f inverse x is equal to y is equal to x by 2. And if you draw the graphs for these 2 straight lines, the given function and its inverse, they are y is equal to 2x and y is equal to x by 2. They are mirror images of one another with respect to the straight line y is equal to x. That's what the theorem talks about. Another important thing that we require this in our engineering is increasing and decreasing nature of functions. Everywhere we use these properties in our engineering and technology. So what is an increasing function and what is an increasing function? In layman's language, as I said, the calculus always talks about the behavior of the dependent variable or the function f of x with respect to the independent variable x. So here also increasing and decreasing functions are the study of the function with respect to x. So when x is increasing, the function increases or decreases. That's what it means. So when x is increasing, the function is also increasing, then we call it as increasing function. When x is increasing, the function is decreasing, we call it as a decreasing function. So then how this idea is defined, let us see. If x1, x2 are 2 points in the domain of f, then f is increasing if f of x1 less than f of x2 whenever x1 less than x2. So as x increases, f of x should also increase. If x increases but f of x decreases. So decreasing if f of x1 greater than f of x2 whenever x1 less than x2. So geometrically you can see this. So on the first diagram, x1 is less than x2, but f of x1 is less than f of x2. Then it is increasing function. It is increasing in nature like this. Okay. But in this case, x1 less than x2, but f of x1 is gradually decreasing. So that's why we call this is a decreasing function. So next idea is, what is the concept of limit? Again, limit concept is somewhat related to the behavior of the function again with respect to x. When the independent variable approaches a particular constant value. I repeat, when the independent variable approaches a constant value, where does this dependent variable or f of x or the function go? What happens to the function? And that's all. That's what all about limits. Concept of limit is a fundamental building block, and all concepts in calculus are based on this concept. For a very clear basic understanding, consider the decimal expansion of 1 by 3. And I'm not going into the definition of classical definition, chase definition of limits, because you are engineering students, you need to have some clear understanding, basic understanding about this. So if a decimal expansion of 1 by 3, if I consider, we know that it is 0.33333 recurrence, which can be expressed as 0.3 plus 0.03 plus 0.003, so on and so forth. How many terms? Because at recurrence, infinitely many terms we have. So if I define Sn as the sum of the first n terms, so that means your S1 becomes 0.3, S2 becomes 0.33, S3 becomes 0.333, so on and so forth. Sn becomes 0.333 up to n terms. Now, as Sn, in Sn, if n is going on increasing, so then what happens? As n goes on increasing, Sn gets closer and closer to the value of 1 by 3. So then what we call it? It is called limit value of 1 by 3 as n increases. Hope you understood it well, right? So the most basic view of limits is to understand the behavior of a function dependent variable as the independent variable approaches a given value or a constant value. So when I say limit x goes to 3, x square minus 2x plus 1, here your function is x square minus 2x plus 1. I want to know where it goes when the independent variable x approaches a constant 3. So clearly if you put x is equal to 3 in this function, we get 9 minus 6 plus 1 comes out to be 4. That is the limit value of this function, and that's where it goes, this function approaches. Okay. The classical definition of a limit of a function now. The limit of f of t as t approaches a constant c is the number L given if given any epsilon greater than 0, there exists a delta greater than 0 such that 0 less than t minus c less than delta, mod f of t minus L less than epsilon. That means it is written as limit t goes to c, f of t is equal to L. Informally, this value of f of t, what does it mean now in our simple terms? If this value of f of t can be made as close as we like to a fixed constant L by assuming t to be sufficiently close to cell. If we can manipulate that, then we say that f tends to L. That means f can be taken as close as possible to the constant value L by assuming sufficiently the values of t which are very sufficiently close to c. If you can do that, then we say that L is the limit of f of t. The above limit is called a two-sided limit. That means when I say on real line, you see the diagram, understand, here t approaches c. That's what we mean, what we call t tends to c. Along real line, c is a constant. I am saying t goes to c. This t goes to c, it can happen in two ways. If you see the diagram here, from the left of c and from the right of c. From the left of t means t less than c. From the right of c means t greater than c. So this t can approach c in both the directions, t less than c and t greater than c. When t tends to c from the right and t tends to c from the left. So if you find the limit when t goes to c from the right, it is called the right limit, and tends to c from the left, it is called left limit. Some functions exhibit different behaviors on two sides of c. For example, if f of x is equal to mod x by x, so for x greater than 0, mod x becomes x, then f of x is equal to mod x by x becomes 1. But for x less than 0, what happens? What is the definition of mod x? Mod x is 1 for x greater than 0, and it is minus x for x less than 0. If you use the definition of mod x, then f of x becomes minus 1. So, if you see the geometrical representation of this function, to the left of 0, the value of f of x is minus 1, and to the right of 0, the value of the function is 1. So, there is a jump here from minus 1 to 1. This is what we engineering students we call direct delta functions, impulse functions, so many things we study with having some jumps. This is a typical example of such functions. If you see here, clearly as t approaches 0 from left, f approaches minus 1, and t approaches 0 from the right, then f approaches 1. These facts are denoted by limit x tends to 0 minus, that means to the left of 0. F of x is equal to minus 1. Limit x goes to 0 plus, that means right hand limit, right limit. Limit x goes to 0 plus of f of x is equal to 1. These are called left and right limits. The limit of t as t approaches 3 from the left equals L if given epsilon greater than 0, there exists delta greater than 0 such that c minus less than t minus delta less than t less than c. That means we are talking about left of c. Implies mod f of t minus L less than epsilon. This is called left limit. Similarly, the limit of f of t as a t approaches c from the right, if so and so, this thing happens. Then the limit of f of t as t as at a exists if and only if. Now we have left limit and right limit. When did we say that the limit of the function exists? That is important thing. That is a test. In fact, that is how we test whether the limit exists or not. So if you consider left limit and the right limit, both of them must be equal. So the statement here is the limit of f of t at t is equal to a exists if and only if both the left and right limits exist and are equal. That means limit t tends to a plus f of t must be equal to limit t tends to a minus f of t is equal to a. Say for example, if you consider this function as we have discussed earlier geometrically, x goes to 0 mod x by x. So 0 x tends to 0 minus, that becomes minus 1, as x goes to 0 plus mod x by x is 1. So limit does not exist because the left hand limit and right hand limit are not equal. So take another example, limit x goes to 3, 4x square minus 17x plus 5, 15 by x square minus x minus 6. So that we can write in a convenient way. You can as well substitute x is equal to 3 there. Otherwise, if you want to put the limit as x goes to 0, we can then x minus 3 or 3 minus x can write in terms of that conveniently. You can see that this limit goes to 7 by 5. So then another problem example is evaluate limit x goes to 2 bracket x. I hope all of you know what we mean by bracket function. This is defined as the integral part of x. That means if I say x is equal, if I take 1.1 and if I want to consider this bracket x function or integral part of x, when x is equal to 1.1, what is integral part? It is 1. So 1 less than x less than 2, the integral part becomes 1. If x is between 0 and 1, the integral part of x is 0. That's what we mean by integral part of x function. So we want the limit as x goes to 2. Let us consider now x go from the right hand limit. We have to show that right hand limit is equal to left hand limit at x is equal to 2. Okay, let us go ahead. Let x goes to 2 plus. That means from the right hand side. That means x is more than 2. Then when x is more than 2, what is integral part of x? 2. When x tends to from the left, so less than 2. That means x lies between 1 and 2. So then integral part becomes 1. So as x goes to 2 plus, the limit is 2, and as x goes to 2 minus, the limit is 1. So that means the right hand and left hand limits are not equal. So the limit does not exist. Another thing is, another standard result we have, limit x goes to infinity, sin x by x, that is 0. So here we have important property on sin x functions, minus 1 less than or equal to sin x less than or equal to 1. For positive x, if you define throughout by x, then minus 1 by x less than or equal to sin x by x less than or equal to 1 by x. Now if you consider the limit x goes to infinity, minus 1 by x becomes infinity. So sin x by x goes to, as x goes to infinity, 1 by x goes to 0. So then sin x by x lies between 0 and 0, then it must be equal to 0. Similarly, limit x goes to infinity, cos x by x also, because cos x also minimum and maximum values, so cos x is also minus 1 and plus 1 respectively. So that is that problem. So I give some problems for you to work out on your own, because we have considered these important ideas of limits. The basic understanding of limits, you have I have given you 5 problems. You can note it down, or you can otherwise you can take a screenshot of this. Otherwise the PPT will be that you will upload it. You can have it later also. That's up to you. So try on your own. Limit x goes to 0, x sin 1 by x. Limit x goes to 1, cube root of x minus 1 by square root of x minus 1. Limit x goes to 2 x power x, so on and so forth. Other problems. Now we will go to another basic important properties of limits. So if limit x goes to a, f of x is plus infinity or minus infinity. That means function is going to infinity or minus infinity as x goes to a approaches. That means then at x is equal to a, the function is going to plus or minus infinity. Then such a line is called a vertical asymptote. You can see in the diagram also, at x is equal to a, the function goes to infinity. So such lines, actually points at which the function goes to plus or minus infinity, are called vertical asymptotes. And I have some more important properties on limits. Limit x goes to a, f of x is equal to L1. Limit x goes to a, g of x is equal to L2. Then limit x goes to a, f plus or minus g is equal to L1 plus or equal to L1 plus or minus L2. Limit x goes to a, f of x into g of x is equal to L1 into L2. Limit x goes to a, f of x by g of x is equal to L1 by L2, provided LT not equal to 0. And then limit x goes to a, nth root of f of x. Then limit can be taken into the nth root. Then nth root of limit x goes to a, f of x, that is nth root of L1 if L1 greater than 0. And limit x goes to a, this is a very standard principle. Most of the problems we will apply in these conditions, these rules directly. So be very thorough with these rules. limit x goes to a, x power n minus a power n by x minus a is equal to n into a power n minus 1. N is a non-zero rational number, and for all a for which a power n minus 1 is defined. Most of the problems and limits, we use these properties. X power n minus a power n by x minus a is equal to limit is equal to n into a power n minus 1 as x tends to a. Similarly, limit x goes to 0, sin x by x is equal to limit x goes to 0, tan x by x is equal to 1 for 0 mod x less than pi by 2, and limit x goes to 0, e power x minus 1 by x is equal to 1. In fact, if you here, you can simply do this problem. If you ask you to solve this problem, as x goes to 0, if you put the limit in the function e power x minus 1 by x, e power 0 is 1, so numerator is 1 minus 1, 0, denominator x goes to 0 becomes 0. So whenever the function, when you put the limit, takes the form 0 by 0 or infinity by infinity, then you cannot evaluate it. Then what we do? We apply an important rule called L'Hospital's rule. L'Hospital's rules, which says that whenever 0 by 0 or infinity or indefinite form occurs when you substitute the limit, then the simple method is differentiate the numerator, differentiate the denominator, then again apply the limit. So here clearly, when you put the limit x goes to 0, numerator is 0, denominator is 0, so 0 by 0 form. Then what we do? Differentiate the numerator, e power x minus 1, derivative is e power x, put the limit x is equal to 0, 1. And if you differentiate the denominator, derivative of x is 1. So limit x goes to 0, e power x minus 1 by x becomes 1. And limit x goes to 0, a power x minus 1 is log a base e. So this is. Next property is limit x goes to infinity is also very important thing. I'm sorry, one power x is missing here. Limit x goes to infinity 1 plus 1 by x whole power x is equal to e, or else limit x goes to 0, 1 plus x whole power 1 by x is e. Similarly, limit x goes to minus infinity 1 by x is 0, or limit x goes to infinity 1 by x is also 0. And limit x goes to plus or minus infinity f of x whole power n is limit x goes to infinity plus or minus infinity f of x whole power n. And these are some basic important properties on limits. Then comes continuity. Limit is the basis, again, is the building block for all the concepts on calculus. So how these limits are useful in continuity, let us see. A function y is equal to f of x is continuous at an interior point a of a domain. That means this point at which we are discussing continuity must be an interior point of the domain. Then if limit x goes to a, f of x is equal to f of a. If the domain AB, if the domain is AB and y is equal to f of x is continuous at left endpoint a, if limit x goes to a plus f of x is equal to f of a. So see, if you see the interval, closed interval AB, you don't have anything on the left of a. And if you don't have anything on the right of b. So there are endpoints of the interval. So if the domain is AB, closed interval AB, and y is equal to f of x is continuous at left endpoint of a, if, that means at a, the right hand limit, and at b, the left hand limit, they must exist. At a, the right hand limit, and at b, the left hand limit. If they exist, it's okay. Then f of x is said to be continuous if it is continuous at each point of the domain. Then how do you test the continuity of a function? Y is equal to f of x is continuous at x is equal to a if and only if first thing is f of x must exist. It should not have any discontinuities or maybe infinite values. Then limit x goes to a, f of x must exist. Then it must be equal to the value of the function at x is equal to a. Observe the difference between this 2 and 3. 2 says limit x tends to a, f of x exists. That means limit exists. must exist. The third one, limit must exist and it must be equal to f of a. That means functional value at a. Then we say it is continuous. Let us see a couple of examples to understand a better way. F of x is equal to x square minus 4 by x minus 2. Discuss the continuity at x is equal to 2. Limit x goes to 2, x square minus 4 by x minus 2 is equal to 4. Okay. And then f of x is equal to mod x. Discuss the continuity at x is equal to 0 and x is equal to a. So limit x goes to 0, mod x is equal to 0 is equal to f of 0. So when at x is equal to a, for a greater than 0, limit x goes to a f of x, that is mod x, because a is positive, mod x is x, so it becomes f of a. For a less than 0, mod x is minus x, so it becomes minus a. So when x is not equal to 0, what is happening here? The right limit is, that means when a greater than 0, the limit is a, and for a less than 0, the limit is minus a. So left limit and right limit are different, so limit does not exist. So f of x and g of x are continuous function at x is equal to there, x is equal to a, then f plus or minus g is continuous at x is equal to a, and f into g is continuous at x is equal to a, and f by g is continuous at x is equal to a if g of x is not equal to 0. They are basic properties. Polynomials are always continuous everywhere. A rational function is continuous at every point where the denominator is non-zero and has discontinuities at the points where denominator is 0. Only thing, when we have rational functions, we have to be very careful with the denominator. The points at which the denominator is 0, there the function is not continuous. If f is 1 to 1 and is continuous at each point of its domain, then f inverse is also continuous. We already have studied a theorem that whenever f is 1 to 1 and then the inverse exists. So here one more additional point here, f is 1 1 and is continuous at each point of the domain, then f inverse is also continuous. Because f is 1 to 1, f inverse exists, and because f is continuous, f inverse is also continuous at each point of the domain. That is the range of f. See another example, fx is equal to x into cos 1 by x for x not equal to 0, and it is defined as 0 for x is equal to 0. Examine the continuity at x is equal to 0. Let us say, let x not equal to 0, then mod f of x minus f of 0 is, f of 0 is defined as 0, so the f of x minus 0 is equal to x into cos 1 by x is equal to mod x into mod cos 1 by x. Because cos function is always less than 1, so mod x into cos 1 by x is less than or equal to mod x. Since mod cos 1 by x is less than or equal to 1. So clearly 0 is less than mod fx minus f of x is less than or equal to x. But limit x goes to 0, mod x is equal to 0. So what happens? This term goes to 0. That means f of x minus f of 0 goes to 0. That means f of x, difference between f of x and f of 0 goes to 0 means, it means that limit f of x goes to 0, f of x is equal to f of 0. What does it mean? Modulus of f of x minus f of 0 is almost all 0 or 0. Then f of x must be equal to f of 0. So that means the limit value is equal to functional value. That is the testing condition for the continuity of a function. We have discussed it earlier. Limit value must be equal to the functional value. Limit x goes to 0, f of x must be equal to f of 0. If this happens, then continuity can be established. So another example, f of x is equal to e power 1 by x plus 1 by e power 1 by x minus 1 for x not equal to 0 and 1 for x is equal to 0. Examine the continuity of f at 0. So limit x goes to 0, f of x is equal to, when x goes to 0, e power 1 by x becomes e power infinity. So it's in the form infinity by infinity. So what I do is, I take e power 1 by x numerator denominator and cancel, then x goes to, what happens, x goes to 0, 1 plus e power minus 1 by x by 1 minus e power minus 1 by x, that is 1 from the right hand side. Then you consider the left limit, limit x goes to 0 minus f of x, then it becomes minus 1. So the left limit and right limit are not equal, the limit itself does not exist, so the function is not continuous. Then examine the continuity of the function at x is equal to 2. So if you consider limit x goes to 2 minus from the left, that means 0 less than x less than 2, this is the function. X square by 2 minus 2. So when you put the limit 4 by 2 minus 2 is equal to 0. This is what we have. And if x goes to 0, x goes to 2 plus f of x. So when x goes to 2 from the right side, the function is defined like this. Okay. So if you find the limit of that, the left limit becomes 0 and the right limit also becomes 0, but limit x goes to 0, f of x is also defined as 0 from this. Then left limit, right limit and everything is equal, so the fx is continuous at x is equal to 2. So another example you can see, f of x is equal to x power 1 by x minus 1. You can go through it very simply. Another example. So some problems for you on continuity also. F of x is equal to x by 1 plus e power 1 by x, so that so on so forth, under 5 problems. Okay. And then next thing, differentiability. So we have finished the limits, continuity, and then we entered differentiability. So what do we mean by differentiability of a function? Let f be a function from D to R. A D is a domain and R is a set of real numbers. Clearly, domain is also a subset of real numbers, real domains we are considering, because we are dealing with real valued functions with real domains. Then D is subset of R. And let A be any point in the domain. Then f is said to be differentiable at A if the limit x goes to A, f of x minus f of A by x minus A exists. Then the limit value is L. Then L is called the derivative of f of t at x is equal to A, and it is denoted by f dash A. So the limit must exist. What is the limit? Limit x goes to J. Just limit x goes to A, f of x minus f of A by x minus A, it must exist. Or in other terms, another way also we write this as limit h goes to 0, f of x naught plus h minus f of x naught by h. So one only difference from the between the previous definition, this definition is that any general x can be expressed as x naught plus h. That's all. Nothing more to say about this. A function which is continuous at x naught may not be differentiable at x naught. So if the function has a limit at a point, then we can talk about continuous. So if the function is continuous at a point, then limit exists. The function is differentiable, the function is continuous. The converse need not be true. That means every continuous function need not be differentiable. When does it happen? Let us see. A function which is continuous at x naught may not be differentiable at x naught. Generally it happens in two ways. At corner points, maybe functions like this. At x naught, this is at x naught, see corner point here. Then at such a point, the left hand derivative and right hand derivative may not be equal. Points of vertical tangency. In such case also, though the function is continuous at the point, it may not be differentiable. Let us say, do some problems, discuss the continuity and differentiability of f of x at mod x. So we have already proved that mod x is a continuous function everywhere. Now we'll discuss the differentiability of this. So f dash 0 means limit 0 h goes to 0 f of 0 plus h minus f of 0 by h as per the definition of differentiability of a function at a point 0. So limit mod h f of 0 plus h means f of x is equal to mod h. So mod h minus 0 by h. If h is positive, this is 1. If h is negative, this is minus 1. So the left of 0, the limit value is minus 1. To the right of 0, the limit value is 1. So right hand derivative and left hand derivative. If you find the limit from the left, it is called left hand derivative. If you find the limit on the right hand side of 0, it is called right hand derivative. Both the limits must be equal. But clearly, it's not so here. The left derivative is not equal to a right derivative. Then, so we say that f is not differentiable. So most important thing is, fx is equal to mod x is a continuous function. We have proved it earlier, but it is not differentiable. It comes under the previous case, mod x function looks like almost like this. If this is x is equal to not 0, of course x is equal to a, it's a corner point. So in such cases, the function cannot be differentiable. But if the function is differentiable, then it must be continuous at x naught. This is all denoted by df by dx, we know that. Then what is the geometrical meaning of this? Y is equal to f of x is a continuous function, then it can be expressed as a smooth curve. F dash at x is equal to x naught is the slope of the tangent line to the curve at fx. So when we take this y equal to f of x, what does this f dash x represent? F dash x at x naught, the slope of the tangent drawn to that curve at x naught. So if you draw a tangent at x naught to the given curve, then the derivative of the function is the slope of the tangent at the point. So f dash x naught is limit x goes to 0 f of x naught plus h minus f of x naught by h is a definition. Or if x naught plus h is equal to x, if you call this as x, then h becomes x minus x naught. So if we remove this, h goes to 0. If h is not tending 0, that means it is approximately equal. If limit h goes to 0 becomes 0, then exactly f dash x is same as right hand side. If it's not so, then they are approximately equal. Then you can write this as h is x minus x naught. So x minus x naught into f dash x naught is approximately equal to f of x minus f of x naught plus epsilon h. If you call this f of x as y is equal to f of x naught plus x minus x naught into f dash x naught plus epsilon. This is, you can say this epsilon h is a constant, f of x naught is a constant. So y is equal to some constant plus x minus x naught into f dash x naught. As I said, f dash x naught represents the slope. So this is m. If you call this as m into x minus x naught is equal to y minus y naught. This is the form y minus y naught is equal to slope into x minus x naught. This is nothing but the point slope form of a straight line. So it means to say that if f dash is the slope, then the equation of the tangent is y minus y naught is equal to m into x minus x naught. This is what we mean geometrically. So let us see. Find f dash 0 if f of x is equal to 1 minus cos x by x for x not equal to 0 and f of x is 0 for x is equal to 0. So limit x goes to 0, f dash 0 definition is limit x goes to 0, f of x minus f of 0 by 0. F of x minus f of 0 by x minus 0. F of 0 is given as 0. So f of x is 1 minus cos x. It can be expressed as 2 sine square x by 2. So the limit is limit x goes to 0, 2 sine square x by 2 by x square. If you multiply divide with 2, then 1 by 2, 4 sine square x by 2 by x square. Then you can write it as 1 by 2 into limit x goes to 0 sin x by 2 whole square. But we know that limit x goes to 0 sin x by x is 1. So if you put x by 2 is equal to some theta, this becomes limit theta goes to 0 sin theta by theta 1. So 1 by 2 into 1 square, the limit value is 1 by 2. So f dash 0 is 1 by 2. So similarly, we have another function f of x equal to 3 plus 2x for minus 3 by 2 less than equal to 0 and f of x equal to 3 minus 2x or so and so that f is continuous at x is equal to 0 but f dash 0 does not exist. It is simple equation of a straight line, but we don't have a derivative at x is equal to 0. Let us see. Limit x goes to 0 from the right of f of x is limit x goes to 0 plus 3 minus 2x. So but that is 3. Because from the right hand side of 0, the function is 3 minus 2x. Okay. And when you take the limit from the left, the function is 3 plus 2x. So limit x goes to 0, 3 plus 2x, limit is 3. So right hand limit and left hand limit are equal. Okay. So what is the functional value? For the continuity, left limit, it must be equal and it must be equal to the functional value. Function value, what is the function value of x? At x less than or equal to 0. And even x is equal to 0, the function value is 3 plus 2x. So if you put x is equal to 0 here, the function value is 3. So left hand limit, right hand limit is equal to functional value. So function is continued x is equal to 0. Coming to the derivative. So f dash 0 is defined as limit x goes to 0, f of x minus f of 0 by x minus 0. So limit again, right hand limit x plus limit 0 plus is the function is 3 minus 2x minus 3 by x is equal to limit x 0 plus minus 2, that is minus 2. But when we consider limit from the left, fx minus f of 0 by x minus 0, that is equal to limit x 0 tends to 0 minus 3 plus 2x minus 3 by x, that becomes 2. So the left hand derivative and right hand derivative, they are not equal. So f dash 0 does not exist. So I have given some more problems here for practice. F of x is equal to x minus 1 by 2x square minus 7x plus 5 for x not equal to 1 and this function is equal to minus 1 by 3 for x is equal to 1. Then find f dash 1. And then f of x is equal to x into mod x. Differentiable at x is equal to test. Is it differentiable at x is equal to 0? So see, we have, this is a very important problem. Standard example. So mod x we have, I am giving you a hint. We have all discussed about mod x. You can take that as a hint. Then decreasing and increasing nature of functions. We have already seen the definitions of increasing and decreasing natures. What is the definition of increasing function? As x increases, f of x must increase. It goes like this. But as x increases, f of x comes down like this, then we call it decreasing function. So for the sake of definition, it's okay. Then how do we test it? What is the condition? How do we test whether given a function is decreasing or increasing? So let us see the important theorem here to test the increasing and decreasing nature of functions. Let f of x be a function that is continuous and closely AB and differentiable and open AB. It must be a differentiable function here. So if f dash x is greater than 0 for all x belongs to open AB, then f is increasing in AB. If f dash x is less than 0 for all x in open interval AB, then f is decreasing. If f dash x is equal to 0 throughout AB, then f is constant. F is a constant function. So if I give you a function, how do you test whether it is increasing function or decreasing function? Find its derivative. The derivative is greater than 0, is positive for all values of x, then it is increasing. If for all values of x it is always a decreasing function, then it is negative for all values of x, then it is a decreasing function. So this is in gate point of view. In gate point of view, sometimes we are getting problems on this also. Like find the intervals. The problems will be like this: find the intervals in which the function is increasing, and what is the interval in which it is decreasing. You will be given some alternatives A, B, C, D. You have to find the intervals, suitable intervals. So such problems I have given here. Find the interval on which f of x is equal to so and so x square minus 4x plus 3 is increasing, and the intervals in which it is decreasing. So for that, the testing condition is first we have to find the derivative. So f dash x. What is the derivative of x square minus 4x plus 3? It is 2x minus 4. So if you want to find the intervals of increasing behavior, then f dash x must be greater than 0. Okay. So when f dash x greater than 0, first you see this, f dash x greater than 0 means f dash x is 2x minus 4 is greater than 0. That means 2x minus 4 greater than 0 means x greater than 0. So f dash x is greater than 0 if and only if x greater than 0. Only when x greater than 0. That means it is increasing only when x is greater than 2. Okay. So decreasing condition is f dash x less than 0. F dash x is 2x minus 4 less than 0 or x less than 2. So whenever x is less than 2, f dash x is less than 0 or f is decreasing. So f is decreasing for x less than 2. X less than 2 means minus infinity to 2, decreasing. F is increasing for x greater than 0 means in the interval 2 to infinity. On what intervals the function execute? Minus 12x plus 1 is increasing. On what interval it is decreasing? So see, first find the derivative. Then 3x square minus 12. You can take 3 common. So x square minus 4 here. Excuse me. If you take 3 common here, x square minus 4, or else you can write as 3 into x minus 2 into x plus 2. To find the intervals of increasing behavior, f dash x must be 0, greater than 0. That means 3 into x minus 2, x plus 2 greater than 0. So r x less than minus 2, or x greater than 2. And f dash x is less than 0 if x lies between minus 2 and 2. Therefore, f is increasing on the intervals x less than minus 2 means minus infinity to minus 2, or x greater than 2, or that means 2 to infinity, and decreasing in the interval minus 2 to 2. Find the intervals of decreasing nature of the function f x is equal to x plus sin x. So here f dash x is 1 plus cos x. For increasing behavior, f dash x must be greater than 0. So f dash x, what is the cos x maximum and minimum value? Maximum value of cos x is 1. When cos x takes maximum value 1, f dash x becomes 2. When cos x takes minimum value minus 1, in that case it becomes 0. For maximum value of cos x, that is 1, f dash x becomes 1 plus 1, 2, that is greater than 0. For minimum values of cos x, that is minus 1, f dash x becomes 1 minus 1, 0. So f dash x is always greater than but equal to 0 when cos x takes the minimum value. Whatever it is, f dash x is not negative. So f dash x is greater than increasing function. Therefore, f is increasing on the interval minus infinity to. On the complete interval minus infinity infinity, the function is only increasing. What does it mean? The function is never a decreasing function. So another important property, geometrical property of the functions is concavity. Concavity. So if you consider a function, the geometric curve like this, when it's in the form like this, just like a cup holding water. If you have a cup like this, it cannot hold water. Okay. A cup like this, it can always store water. So such a cup which holds water or any substance, any material, that is called, we call that curve as concave up. If it is downwards, it's called concave down, spills water. Holds water and spills water, it is for easy understanding and remembrance only. It's not in the classical definition, we don't say which holds water, which spills water. Okay, the concave up or concave down. So geometrically we can see a couple, geometric structure like this or this. Then how do you put it in terms of words, or how do you test this up or down? Let us see. F of x is differentiable on AB, then f is said to be concave up in the interval AB if f dash x is decreasing on AB and is concave down if f dash x is decreasing on AB. F dash x decreasing on AB, concave up, concave down. F is said to be concave up if f dash x is decreasing, and concave down if f dash is decreasing. So concave up, it should be increasing here. Whenever f dash x greater than 0, so f dash x increasing means f double dash x must be greater than 0. Here it is increasing, it is wrongly written here. F dash x is increasing in AB. That's what I am confusing. Somewhere mistake, right? Okay, I'm sorry for this. I'll correct it and give the PPT. F dash x increasing means fx increasing when f dash x greater than 0. F dash x increasing when f double dash x is greater than 0. So fx is concave up if f double dash x is greater than 0, concave down if f double dash x is less than 0. These are the conditions. Discuss the concave nature of f of x is equal to x square minus 4x plus 3 in the interval minus infinity to infinity. So first find f dash x. F dash x is 2x minus 4. And then you have to find the second derivative. What is f double dash? It is 2x minus 4. This derivative is 2. It is always positive. So f double dash is greater than 0. When f double dash is greater than 0, what is the property we have? F double dash is greater than 0, it is concave up. So what happens to this? F is concave up. Discuss the concave nature of f of x in the interval minus infinity infinity. So x cube minus 3x square plus 1. F dash x is 3x square minus 6x. So find the second derivative. F double dash x is 6x minus 6. So concave up, the condition is f double dash x greater than 0. So when f double dash x, that is 6x minus 6 is greater than 0, means that x greater than 1. So that means whenever x is greater than 1, then f double dash x is greater than 0 or f of x is concave up in the interval 1 to infinity. What happens when x less than 1? When x is less than 1, f double dash x is less than 0. That means f becomes concave down for x less than 1. X less than 1 means minus infinity to 1. In the examinations you may be asked to find the intervals in which the function is increasing, the function is decreasing, or the function is concave down or concave up, so on and so forth. So be very careful with these conditions. So sometimes either it is increasing or decreasing, nothing happens, neither decreasing nor increasing. Then such a point at which the function changes its concavity is called point of inflection. The path x0, the point x0 f x0, it is the point x0 f of x0 at which the function changes the direction of its concavity. See, at x0, let us see, the function here is concave down, and here it is, from here onward it is concave up. So such point at which the function changes its direction of concavity is called point of inflection. In the above problem, fx is concave down in the minus infinity of 1 and concave up in 1 to infinity. That means this problem. I am talking about this problem. For x less than 1, that means minus infinity up to 1, it is concave down like this. 1 onwards, it is concave up like this. So the curve is like this. It is concave down, concave up. The point at which it changes, that is called point of inflection. Discuss the increasing, decreasing, concave up, down, and locate inflection points of x is equal to x plus f of x is equal to x plus 2 sin x in the interval 0 to 2 pi. First thing is you have to find f dash x, that is 1 plus 2 cos x. So increasing, decreasing behavior, we have to, based on f dash x, the sign of f dash x. So observe f dash x is greater than 0. Why? Whenever x is 1, maximum value of x, it is positive. Whenever x is minus 1, then what happens? 2 cos x becomes minus 2. F dash x less than 0. Okay. So observe that f dash x is greater than 0 if cos x is greater than minus 1 by 2. Okay. That means in the interval, whenever this cos x is greater than minus 1 by 2 is 0 to 2 pi by 3 or 4 pi by 3 to 2 pi. And f dash x is less than 0 in the interval 2 pi by 3 to 4 pi by 3. Therefore, f is increasing in the interval 0 to 2 pi by 3 and 4 pi by 3 to 2 by 3 and decreasing in the interval 2 pi by 3 to 4 pi by 3. That's about decreasing and increasing nature. Then for the concave nature, concave up or down, we have to find f double dash x. F double dash x is minus 2 sin x. Minus 2 sin x. So when sin x is positive, f double dash x is negative. Minus 2 sin x. So concave down. When does this sin x is negative? Pi to 2 pi. Third quadrant and fourth quadrant, sin is negative. Whenever sin is negative, f double dash is positive. So f double dash x is greater than 0 whenever sin x is negative. That means x is in the third and fourth quadrant, that is pi to 2 pi, interval pi to 2 pi. On the other hand, if x is in the interval 0 to pi, you know all silver teacups, we have learned that, right? In the first and second quadrants, sin x is positive. First and second quadrants means x is between 0 and pi. Whenever x is between 0 and pi, sin x is positive. So f double dash x becomes minus 2 into positive quantity, that is minus value. So f double dash x becomes less than 0. So it is concave down. And f double dash x changes sign as we pass through pi. Pi to 2 pi, it is concave down. Pi to 2 pi, it is, concave up. 0 to pi, it is concave down. That means 0 to pi concave down, pi to 2 pi concave up. Where it is changing? At x is equal to pi. So x is equal to pi is called the point of inflection. You may be also asked to find the points of inflection. Discuss the concave, concave down, concave up, locate points of inflection. So f dash x is equal to 3x square minus 12, f double dash x is 6x, greater than 0 always, so it's always concave up in the interval 0 to infinity. F double dash x is less than 0 whenever x is less than 0. So in the interval minus infinity to 0, f double dash x is less than 0, so concave downwards. Then at 0 it is changing direction, so 0 is the point of inflection. So under set of problems are given as exercise here. So with this, I think we have considered limits, continuity, and basic differentiation. You are good at differentiation in order to go to intermediate mathematics now, because we are gearing up for GATE and stipulated period of 12 or 14 classes for the complete mathematics. We cannot go into differentiation. So we are talking about the applications of differentiation, like increasing, decreasing, concavity, so on and so forth. So then we talk about integrals. A function f is called antiderivative of a function f on a given AB into open interval AB if f dash x is equal to f of x. A function capital F is called antiderivative of a function f on a closed open AB if f dash is equal to f of small f of x. So for example, if capital F is taken as 1 by 3 x cube, it is antiderivative f of x is equal to x square. Why? Because f dash x is, capital F dash x is 3x square into 1 by 3, that becomes x square. So d by dx of f of x is equal to f of x. T and amount saying that d by dx of capital F of x is equal to f of x. Then integral of f of x is equal to capital F of x plus c, and c is arbitrary constant. And we have discussed already about the arbitrary constants in parameter. It is clearly defines a family of functions. When the arbitrary constant, it can take any value. As you change the value of c, different curves are generated. So this capital F of x plus c is a family of functions. So you know that integration basically it means summation sign. So in integral calculus also we have so many formulas, so many principles, so many rules, and very difficult to finish off in stipulated time. So what I am doing is I am giving a list of all standard formulae here for immediate reference. Say sin x, cos x, tan x, secant square, 1 by a square plus x square, 1 by a square minus x square, 1 by square root of a square plus x square. So many things, so many formulae we have in integral calculus. I have given all these formulas, collected all those things and put it in as an immediate reference to you all. So now the important thing here is not the integration is one aspect, the applications of integration again. As I said, it is very difficult to complete the complete integrals here. So just I am giving the formulas, and practice I will leave up to you. We have to do that. Then what is an integrable function? First let us say the classical definition. A function f is said to be integrable on a closed interval AB if limit maximum of delta xk greater than 0, summation of k from 1 to n, f of xk star delta xk exists. Depend on the choice of partition of xk star in the subintervals. In such case, the limit exists, and then summation is denoted by integral a to b f of x dx. This is called definite integral. Some important rules of definite integration. Integral a to a f of x dx is equal to 0. You know that. Integral a to b f of x dx is equal to, if you interchange the limits, it becomes minus b to a. That means whenever you change the upper limit and lower limit, there will be change of sign. That is a way we have to remember that. Integral a to b is c into f of x dx is c times integral a to b f of x dx. Then integral a to b f x plus or minus gx dx is equal to integral a to b f of x dx plus or minus integral a to b j of x dx. If c belongs to AB, open interval AB, then integral a to b f of x dx can always be expressed as integral a to c f of x dx plus integral c to b f of x dx. A function f is defined in interval is said to be bounded on the interval. If there is a constant here, this is a continuation. If there is a positive number m such that mod f of x is less than or equal to m, or minus m less than or equal to f of x less than or equal to m. And if f is not bound on AB, then it is not integrable on AB. So this is a very important rule here. If f is not bounded on closed AB, what do you mean by bounded? If mod f of x is less than or equal to m for all x in the interval, then we say that it is bounded. Or else you can write minus fx lies always in between minus m and m. M is positive number. Then we call f of x is bounded. When f of x is bounded on AB, you can find the integral. If it is not bounded, then it is not integrable on the interval. So definite integral properties you can do, and then the important thing after definite integrals is improper integrals. Sometimes we have many problems in improper integrals. Sometimes not possible to find some of the integrals also. We take the limit concept, we take the help of limits again to evaluate improper integrals. Sometimes we use beta and gamma functions to evaluate integrals. Sometimes we use Laplace transforms also to evaluate improper integrals. Sometimes we use Fourier transformations. So many tools we use to evaluate the improper integrals. Why? Because it is in the structure of the improper integrals itself. Then what is the general structure of the improper integrals? What is the improper integral? Till now we focus on integrals and different integrals with continuous integrands. Integrand means the function that is to be integrated, that is called integrand. If the integrand is a continuous function, then we have done it in integrals and different integrals. And in different integration, if the integral a to b is a finite interval, with a finite interval or the integrand is continuous function, we could do successfully. Now we extend these concepts to integrals with infinite intervals of integration, and other case is integrands that become infinity within the interval. Such integrals are called improper integrals. So I repeat, first case is the limits of integrations, the length of the interval of integration is infinity. That means integrals, the upper and lower limits may be plus infinity, minus infinity, or 0 to infinity, or minus infinity to 0, or minus infinity to some constant. Like that, the limits will be there. The other way, f of x goes to infinity at certain points. Such cases, we call the integrals as improper integrals. So more clearly, improper integrals arise in different ways. The integrals of the form integral a to infinity f of x dx, minus infinity to 0 f of x dx, minus infinity f of x dx, infinite lengths of intervals. The other way is integrands having discontinuities within the interval of integration. That means integral 0 to a dx by x square. It's not a to a actually, 0 to a. At 0 what happens? 1 by x squared becomes infinity. Such a problem. 1 to a dx by x minus 1. Integral 0 to pi tan x. What happens at tan x? At x equal to pi by 2. It goes to infinity. So integrand goes to infinity. That is second nature. Integral, sometimes integrals involving both the things. That means the length of interval is infinite and the function is, the integrand also goes to infinity at certain points. That is a third class of problems, a combination of the previous two cases. So any of this type of integral is called as a improper integral. Then how do we evaluate these improper integrals? Given when it is in the form integral a to infinity f of x dx, then we express that improper integral as, in place of infinity, we consider some finite constant b. So the integral now becomes a to b f of x dx is a definite integral. We can evaluate it. Once it is evaluated, then let this b go to infinity. Then what happens? Limit b goes to infinity, integral a to b f of x dx means it is same as integral a to infinity f of x dx. This is how we evaluate. First we evaluate the definite integral from a to b, then let this b go to infinity. If the limit exists, then improper integral is said to converge and the limit is the value of the integral. The limit does not exist, then improper integral is said to diverge and the integral is not assigned a value. Then improper integral does not have a value. You cannot evaluate it. So all these methods, beta gamma functions, Laplace, Fourier, Fourier transformations, Laplace transformations, all these tools are used to evaluate the improper integrals. Let us see. See, in fact, you can 1 by x power p, you can integrate very easily between the limits 1 to infinity. But for easy understanding, I am giving an example, but you can extend this to difficult problems also. So, for what values of p, you may be directly asked a problem like this. At some time, in some national level examination like CSIR, JRF net, a couple of times this question was asked earlier. If I don't know about, I'm not so particular about gate examination, but in JRF net or so, this question was asked sometimes. For what values of b does the integral 1 to infinity dx by x power p converge? So 1 by infinity dx by x power p, I can write this as limit b goes to infinity integral 1 to b dx by x power p. So or else limit b goes to infinity. Now I can evaluate this 1 to b 1 by x power p, that is 1 by 1 minus p into x power 1 minus p, and between the limits 1 and b. If you put the limits, upper and lower limits, then it becomes limit b goes to infinity b power 1 minus p minus 1 by 1 minus p. Okay. So if p greater than 1, b power 1 minus p goes to 0 as b goes to 0. So when p is greater than 1, then 1 minus p is less than 0. Isn't it? When b power something is less, when b power 1 minus p, where 1 minus p is less than 0, and as b goes to infinity, this b power 1 minus p goes to 0. That means 1 by infinity dx by x power p is, this term goes to 0, then the remaining term is 1 by p minus 1. Okay. So limit exists. So the value of the improper integral is 1 by p minus 1. What happens if p is less than 1? When p is less than 1, b power positive quantity. So as b goes to 0, limit is not finite. So another problem, integral 0 to infinity 1 minus x power 1 minus x into e power minus x dx. So 1 minus x e power minus dx is, the integral is x into e power minus x plus c. First you can integrate this, x e power minus x plus c. So 0 to infinity 1 minus x e power minus x dx is, limit b goes to infinity, 0 to b 1 minus x e power minus xt, but integral of 1 minus x e power minus x is x e power minus x plus c. So if you put the limit 0 to b as b goes to infinity. So limit b goes to infinity, if you put b e power minus b. Okay, the c becomes, upper limit it is c, at lower limit it is c minus c becomes 0. So this is in the form as b goes to, this is b by e power b. b by e power b. As b goes to infinity, it is in the form infinity by infinity. So then if you apply L'Hospital's rule, then becomes 1 by e power minus b with a negative sign. So then if b goes to infinity, the limit is 0. Therefore 0 to infinity 1 minus x e power minus x dx becomes 0. This is how we evaluate the improper integrals of the first type. And coming to the second type of the improper integral, that means integrands having infinite or discontinuities. Let us say f is continuous and closed AB except for a infinite discontinuity. At certain points in the interval at which the function goes to infinity. That is the case here. Integral a to b f of x dx, k to b minus 1 f of x. If the limit exists, then the improper integral is said to have a limit. So, this is the problem. 0 to 1 dx by square root of 1 minus x. X is equal to 1, what happens? When x is equal to 1, the function goes to infinity. So that is an issue here now. The function is having a discontinuity at x is equal to 1, or goes to infinity at x is equal to 1. Therefore, we slightly modify the limits. We write integral 0 to 1 as limit s bit smaller than k, smaller than 1. Okay. So we write 0 to k and k goes to 1 minus. It is k does not go to 1. K is not equal to 1. Something epsilon less than 1. The problem is at k is equal to 1 or x is equal to 1. So x not equal to 1, something less than 1. Let that something less than 1 must be k. So k less than 1 minus 0 to k integral dx by square root of 1 minus x. Then integrate this 1 minus 2 square root of 1 minus x between the limit 0 to k. So put the limits we have at x as k goes to 1 minus, the limit goes to 2. This is what we do in problems of this type. So similarly, if you take the problem integral 1 to 4 dx by x minus 2 power 2 by 3. Clearly at x is equal to 2, the function goes to infinity. And x is equal to 2 lies in the interval 1 to 4. This is a problem. So in such case, we divide this problem into, split this problem into known integrals. So we write this I as 1 to 2 dx by x minus 2 whole power 2 by 3 plus 2 by 4 dx by x minus 2 power 2 by 3. And for this, we write this limit k goes to 2 minus 1 to k dx by x minus 2 power 2 by 3. And this straight if we have any we don't have any discontinuity here. So straight away you can integrate this. This is the value of that. So if you evaluate this, you will get in terms of k, and then k goes to 2 minus. This is the limit we get. That's how we evaluate the integrals of this one. So some problems for practice. Do it. 0 to infinity e power minus x dx, minus infinity to 2 dx by x square plus 4, integral 0 to 1 dx by 2x minus 1. Find a positive value of e such that, I think this problem was asked earlier in GATE also. 0 to infinity dx by x square plus a square is equal to 1. And another important thing is, this is completely an engineering application. Length of arc, areas and volumes using integration. The first thing is length of an arc. So you can find, you know how to find length of a straight line. If you have a simple scale, just you can measure the length of a straight line. And if you know the 2 points, endpoints of a straight line, you can, if we let us say x1, y1, x2, y2 are the 2 endpoints of a straight line, you can find the length of the straight line by x2 minus x1 whole square plus y2 minus y1 whole square under root. You will find the straight line equation. But instead, we have a curve like this. We have a curve like this. Then how do you find the length of this arc? Then that's where we use this integration to find the length of the arcs. Let y equal f of x be a smooth curve on closed AB, or f dash b must be continuous on closed. That's what actually we mean by smooth curve. F dash b continuous on closed AB. Then length of the curve or the given interval is called the arc length of f. Arc length of f over closed interval AB. Arc length means along the arc, length along the arc. It's not just, it is first initial point is end point between the curve like this. It's not just finding the distance between the two endpoints. It is same as length of the line joining the 2 points. What we want? The length of the arc. Just like the perimeter of the circle. Okay. So if you want to find the length of the curve, you have to find along the curve. Then we use integration to find this. Just to avoid much of mathematical complications, straight away I give the forms, different forms available to find the length of the arc. If y of x is a smooth curve on closed AB, then arc length of f over the AB is L is equal to integral a to b square root of 1 plus f dash x square. This is a direct formula we have for that. Similarly, if the curve is in the form x is equal to g of y or the interval CD, then L is equal to integral c to d square root of 1 plus g dash y d square dy. In parametric form, if the curve is in the form x is equal to x of t and y is equal to y of t and t is varying from t1 to t2, then the length of the arc length is given by integral t1 to t2 square root of dx by dt whole square plus dy by dt whole square. For example, the parametric representation of a parabola y square equal to 4ax is 280 and 80 square. You know that y square equal to 4ax is parametric representation is 80 square 280. X is equal to 80 square, y is equal to 280. So in such case, find the dx by dt, x is equal to 80 square, find the dx by dt, find dy by t, then straight away put it in the formula, you get the length of the arc between t1 and t2. Then another form we have is polar form. The polar form is one important representation of coordinates. We have three Cartesian systems we know, x-axis, y-axis, and any other point is general point is in the plane is denoted by xy. Two-dimensional space, two-dimensional, you can say planar region. Another way of representing planar curves is polar curves, r and theta. And any general point in plane is denoted by r comma theta. What is r? R is equal to square root of x square by y square. And theta is line joining the point with the horizon. This line, and this is x-axis, y-axis, we have like this, and this is the point. If you join the point like this line, the length of this line is r, square root of x square plus y square. And this line makes an angle theta like this. This is theta. Okay. So from the right angle triangle, we get x is equal to r cos theta, y is equal to r sin theta. See, this is the x-axis, y-axis. I have a point here. Join this point like this. Okay. So this becomes like if you drop a perpendicular on x-axis like this. This is a right angle triangle now. Okay. This is a right angle triangle now. So this is theta, and from the right angle triangle now we know that x is equal to r cos theta and y is equal to r sin theta. So this polar representation of a point x is equal to r cos theta, y is equal to r sin theta. When the curve is expressed in terms of this r and theta, here r is equal to square root of x square plus y square and theta is equal to tan inverse y by x, then the length of the arc is L is equal to theta 1 to theta 2 integral of square root of r square plus dr by d theta whole square d theta. If the curve in the polar form other way, theta is equal to f of r, theta is equal to f of r, then L is r1 to r square root of 1 plus r square d theta by dr whole square dr. Please, there is a lot of confusion between these two things. Generally, students get confused between this expression and this expression. Be very careful with this. Okay, but these are very two important formulae in polar form. So, two-dimensional planes, we have two representations. One is Cartesian systems, and the other important thing is polar representation. Similarly, for three dimensions also we have Cartesian form, the x-axis, y-axis, z-axis, and two more things we have: cylindrical coordinate system and spherical coordinate system. Cylindrical coordinate system and spherical coordinate system. We discuss these things while discussing multiple integrals. Okay. For the time being, for the length of the arcs in a plane, polar form is enough. We need not worry about cylindrical and spherical coordinate systems. So, some problems on this. Find the length of the curve 8x is equal to y power 4 plus 2 y power minus 2 between y is equal to 1 and y is equal to So clearly, if you take it's in the form, the curve in the form x is equal to g of y, where g of y is 1 by 8 y power 4 plus 2 y power minus 2. So for the formula, to use the formula, we need to have here. So because the curve is in the form x is equal to g of y, we need to find g dash y. Okay. So dx by dy or g dash y is 1 by 2 y cube minus 1 by y cube. So substitute this in the formula L for arc length. The given points are y is equal to 1 to 2. So this becomes 1 to 2 square root of 1 by 4 square of this. 1 by 4 y cube minus 1 by y cube whole square. Okay, substitute in the simple substitute in the formula. So if you integrate the whole thing, you square it and integrate the whole thing, this is what we get, 33 by 16. Now, this second example is given in parametric form. Find the length of the curve, the parametric form of the curve, x is equal to e power minus t cos t, y is equal to e power minus t sin t. Okay. In the interval 0 to less than or equal to t, less than or equal to pi by 2. Again, what is the formula for the parametric representation? This is what we have. We need to find dx by dt whole square plus dy by dt whole square. So dx by dt is e power minus t into derivative of cos t, that is minus sin t, derivative of e power minus t into cos t. So dx by dt is minus of e power minus t into cos t plus sin t. And dy by dt is e power minus t into sin, derivative of sin t is cos t, and sin t into derivative of e power minus t minus e power minus sin t. So dx by dt and dy by dt are obtained. So dx by dt whole square plus dy by dt whole square becomes e power minus 2t, e power minus t whole square. Here also we have e power minus t square. So that becomes e power minus 2t cos t plus sin t whole square plus cos t minus sin t whole square. Okay. 2 cos t sin t minus 2 sin t cos t get cancelled. Cos square plus sin square 1, cos square plus sin square 1. So 2 e power minus 2t. So now L is, what is the formula we have? Integral t1 to t2 dx by dt whole square plus dy by dt whole square under root. Okay. So 0 to pi by 2 square root of 2 e power minus 2t dt. So evaluate, this is the value of that. This is parametric form. The other function now, other problem is given in polar form. Find the length of the spiral r is equal to e power I theta from the pole to the point r theta. Pole means 0, 0, r is 0, theta is 0. Okay, r theta is 0. So the formula here is in the form r is equal to f of theta. So the formula is L is equal to theta 1 to theta 2 square root of r square dr by d theta whole square. So for that we need to calculate first dr by d theta. Dr by d theta is r is e power a theta. So a into e power a theta is substituted here in this. R square is e power a theta whole square, and dr by d theta whole square a square a e power a theta whole square. So if you take e power a theta out, then e power a theta and square root of 1 plus a square. So now put it in the formula L is equal to square root of 1 plus a square can be taken outside, is a constant, square root of 1 plus a square. The limits of integration from the pole to 0 to theta. So pole means theta is 0 to theta of this thing, that is e power a theta. So if you simplify this, we get like this. This is how we do the problem in to find the arc length of a curve between the given limits. So coming to the areas and volumes, that will be discussed very shortly, maybe next class in the multiple integrals. Anyhow, I have given this topic as arc lengths, areas and volumes, that we will discuss in next class. First we finished off. Meanwhile, the point in putting it in next class is not is any great. Till now we are talking about one-dimensional functions. Y is equal to f of x, only one independent variable. R is equal to f of theta, only one independent variable. Coming to the partial differentiation, we have more than one independent variable. Coming to multiple integrals, areas, more than one independent variable. So today I want to focus only on functions of only one independent variable. Okay, that's why I'm finishing off the similar concepts. So coming to mean value theorems. So the first mean value theorem is Rolle's theorem. Rolle's theorem in fact is a basis for the complete theory of numerical methods. Such a wonderful concept. So let us see what this mean value theorem talks about. Consider a function from closed AB to R, and f is continuous at every point of the closed interval AB and differentiable throughout AB, open interval AB, and at endpoints the functional value is same, f of A is equal to f of B. Then there exists at least one point C in open AB such that f dash C is equal to 0. That is a Rolle's theorem. So verify Rolle's theorem and find an appropriate constant for the function square root of 1 minus x square in the interval minus 1 to 1. So clearly, because f is continuous in minus 1 to 1 and differentiable in minus 1 to 1 respectively, and if at minus 1 square root of 1 minus x square has the same value as at x is equal to 1. So f of minus 1 is equal to f of 1. So all the conditions of Rolle's theorem, continuity, differentiability, and f of A is equal to f of B are satisfied. Hence by Rolle's theorem there exists a point C such that f dash C is 0. Okay. So we have to find that point C at which f dash C is 0. So let us say by Rolle's theorem we have f dash C is equal to 0. But what is f dash C? 1 by 2 root 1 minus x square into minus 2x. If you cancel 2, we get minus c base square root of 1 minus c square is equal to 0. So c is equal to 0 clearly satisfies f dash c is equal to 0. So clearly c belongs to this interval minus 1 to 1. So that is value of c is equal to 0. Verify Rolle's theorem of the function fx is equal to x cube plus x square minus x plus 1 in the interval minus 1 to 1. Because the polynomial function is always continuous, always differentiable, we know that. So the first two conditions of Rolle's theorem are clearly satisfied. And then third condition, f of A is equal to f of B. At x is equal to minus 1. The value of this is minus 1 plus 1 plus 1. So the value is 2. And at x is equal to 1, these two things will be cancelled. Then x cube plus 1, that is 2. F of minus 1 is equal to f of 1. So all the conditions are satisfied. Then f dash c is equal to 0. So what is f dash x? 3x square plus 2x minus 1. So f dash c is 3x square plus 2x minus 1. If you take the fractions, you exclude the fractions, 3x minus 1 into x plus 1. So f dash x is 0, x is equal to 1 by 3 or x is equal to minus 1. Clearly x is equal to 1 by 3 lies in the interval minus 1 to 1. So thus there is a c that is 1 by 3 in the minus 1 to 1 for which f dash c becomes 0. That verifies Rolle's theorem. Then some problems on Rolle's theorem. Verify Rolle's theorem for the following functions: fx is equal to sin x by e power x, x minus a power m into x minus b power n, x square in the interval minus 1 to 1, x into x plus 3, e power minus x by 2 in the interval minus 3 to 0. So practice for you. Next important theorem is Lagrange's mean value theorem. It says the first two conditions are same. F of x is continuous in closed AB, differentiable open AB. Then there is at least one constant c such that f of b minus f of a by f of b minus f of a by b minus a is equal to f dash c. So this is the result of this. So verify Lagrange's theorem for the function Lx square plus mx plus n in the interval AB. Again, this is a polynomial function in x, so clearly always continuous and differentiable, we need not verify it. So by Lagrange's mean value theorem, there will be a c in the open interval AB such that f of b minus f of a by b minus a is f dash c. What is f of b minus f of a? lb square plus mb plus n minus la square plus ma plus n. So that n cancels, and then the remaining thing is L into b square minus a square plus m into b minus a by b minus a, f of b minus f of a by b minus a. So clearly b minus a can be taken out common in the numerator, you can cancel it. Then what we get? B plus a into L plus m. Okay. Or L into b plus m is equal to f dash c. What is f dash c? F dash 2l m plus n. That is at c, f dash c is 2lc plus m. So on the left we have L into b plus a from this. L into b plus a plus m. On the right we have 2lc plus m. So m gets cancelled. So your c is, L also gets cancelled. So c is b plus a by 2. Clearly it lies in the interval a to b. That problem. Verify Lagrange theorem for e power x in the interval 0 to 1. If exponential function is always continuous and differentiable, you need not verify it. So f dash c is f of b minus f of a by b minus a. So f dash c is derivative of e power x is e power x. So f dash c is e power c. F of b is e power 1. F of a is e power 0, that is 1. B minus 1 is 1 minus 0. So e power 1 minus e power 0, e power e minus 1 is equal to e power c. So what is c? Log e minus 1. Log e minus 1, if you calculate that, comes out to be 0.5413 is in the interval 0 to 1. So Lagrange mean value theorem is verified. You can find a c like that. The problem will be, you will be asked to find the value of c using Lagrange's mean value theorem in the interval. Okay. So fx is sin inverse x in the interval 0 to 1. The similar way, if it is differentiable and continuous for all x, therefore conditions of Lagrange value theorem are satisfied. So f dash c is derivative of sin inverse x is 1 by square root of 1 minus x square. So f dash c is 1 by square root of 1 minus e square is equal to f of b minus f of b, sin inverse b minus sin inverse 0, that is pi by 2. So c is equal to square plus or minus square root of pi square minus 4 by pi comes out to be 0.7712, lies in the interval 0 to 1. So that is the c of Lagrange's mean value theorem. So another important problems may be like this: x greater than 0, prove that x plus 1 by x is less than. So in the examination the problem may be like this: for x greater than 0, log 1 plus x lies between x plus 1 by x and x minus x by 1 plus x. Different alternatives may be given to you. Okay. So for that, when a problem is given like this, you have to apply Lagrange's mean value theorem. Okay. So how we apply Lagrange's mean value theorem is f of x is equal to f of 0. This is another form of Lagrange's mean value theorem. F of x is equal to f of 0 plus, remember this is another form of Lagrange's mean value theorem. F of 0 is f of x minus f of 0 by x. That's all. F of b, that means if you apply Lagrange's mean value theorem 0 to in the interval 0 to x, f of x minus f of 0 by x. Okay, f of x minus f of 0 by x is f dash c. F dash c is f dash theta h. Okay. So f of x is log 1 plus x. F of 0, and that means log 1 plus x is equal to 0 is log 1 is 0 to x by 1 plus theta x. So for theta less than 1, x greater than theta x greater than 0. So 1 plus x greater than 1 plus theta x greater than 1. So or else x by 1 plus x less than x by 1 plus theta x less than x. But x by 1 plus theta h is log 1 plus x. Okay. So that means x by 1 plus x is less than log 1 plus x less than x. So that's how we can use Lagrange's mean value theorem to establish some inequalities. and exercise is given to you on Lagrange's mean value theorem. So we have generalized mean value theorem here. That is what we call Taylor's theorem also. I have 5 more minutes time. I will explain this Taylor's theorem and we'll do some problems and go to the next topic in this class. Suppose a function f of x satisfies the following two conditions. F of x and its first n minus 1 derivatives are continuous in closed AB, and n minus 1 derivative is differentiable in closed AB, open AB. N minus 1 derivatives, the first n minus 1 derivative, that means f dash, f dash, f double dash, f triple dash, f fourth derivative, fifth derivative, up to n minus 1 derivatives are continuous in closed AB, and n minus first derivative of x is differentiable in open AB. Then there is a point C in AB such that f of b is equal to c f of a into b minus a, f dash a, b minus a whole square plus by 2 factorial f double dash a, so on and so forth. This is Taylor's theorem. If you put b is equal to x and a is equal to 0 in Taylor's theorem, we get Maclaurin's theorem. It takes the form f of x is equal to f of 0 plus x into f dash 0 plus x square by 2 factorial f double dash 0, so on and so forth. This is a very important theorem. We have some problems already in the previous examinations, GATE examinations. Some expansions of certain functions are asked on using Maclaurin's series. Okay, remember this form, very clear, very important. So f of x is f of 0 plus x into f dash 0 plus x square by 2 factorial f double dash 0 plus so on and so forth, x power n by n factorial f nth derivative of this thing. It's called Maclaurin's expansion about x is equal to 0. Find the expansion of tan inverse x, or tan inverse x is equal to tan is pi by 4 plus x minus pi by 4 by 1 plus pi square by 16, so on and so forth. So Taylor's expansion at pi by 4, f of x is equal to f of pi by 4 plus x minus pi by 4 f dash pi by 4. Just I am substituting the values in Taylor series. So f dash x is tan inverse x, f dash x is derivative of tan inverse x 1 by 1 plus x square. So f dash pi by 4 is 1 by 1 plus pi square by 16. F double dash x is minus 2x by 1 plus x square whole square. So f double dash pi by 4 is so on and so forth. So using all these things in the Taylor's theory, we get the given expansion. Okay. Obtain Taylor's series expansion of f of x equal cos x at x is equal to pi, about x is equal to pi by 3, and find the value of cos 61. F of x is equal to cos x. Expansion is Taylor's expansion is given like this: f of pi by 3 plus x minus a by 1 factorial f dash pi by 3, so on and so forth. You can put like the summation form. So f of pi by 3 is 1 by 2, fn is cos x plus n by 2. So put this form, this is a series form, you can go through it. Expand log x in the powers of x minus 1. Evaluate e log 1.1 base e correct to 4 decimals. So f dash x is 1 by log x is f dash x when log x fx is log x is 1 by x, and f dash 1 is 1. F double dash x is minus 1 by x square, f double dash 1 is minus 1. F triple dash is 2 by x cube, f triple dash 1 is 2, so on and so forth. If you substitute these things in the log series, the Taylor series, this is the expansion of log x. Putting x equal to 1.1 in this, you can find the approximate value of log 1.1 as 0.0953. E power sin x using Maclaurin series. Some problems for you on Taylor series and Maclaurin series. So it's not almost all 1 minute short of 12:30. So we have done today limits, continuity, differentiability of one variable functions y is equal to f of x, and then integration, definite integration, improper integrals, and then application of integrations to lengths, that is arc length. Okay. Then we have considered mean value theorems, Taylor's, Lagrange's, what is that? Rolle's theorem, Lagrange's mean value theorem, Taylor's theorem, and Maclaurin's theorem. Okay. So I log off here now, sign off here now with this, and tomorrow class again at 10:30 we will take up local maxima, minima, partial differentiation, okay, all these concepts in the next class. So practice some more all the problems that I have given to you, okay. So good luck, see you tomorrow.